Whoa, 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 whoa. Oh my god. Alright, so for this video, you can tell I'm wearing the same shirt. I probably should have tried to get another shirt, but I'm too lazy for that. We're going to do another problem and it's the same day. So, we have this problem. We have an array of nums. So first off, I want to say code is in the description. The code is in the description for this problem, for this walkthrough. You can reference that, you can look at this, either of them. Our question is range sum query. So we're given an array, and here are the indices. Let me write them. This is index 0, that is index 1, that is index 2. If I ask you what is the sum of the items from index I to j inclusive, what is the sum of that range? So if my I is 0 and my j is 1, what would the answer be? Well, the answer would be the sum of the items going from index 0 to index 1, inclusive. So this is inclusive. So we do 1 plus 2. We stay within the boundaries. The answer is 3. So let's do another example. So if I equals 1 and j equals 2, we go from index 1 to 2. 2 plus 3 is 5. So 5 is the answer for the range sum query 1 to 2. So what is the difficulty in this question? Why don't I just have a linear time solution every time a caller says, hey, I want the range sum from 0 to 2. I want the range sum from 0 to 1, from 1 to 2. Why don't I just count from 0 to 2, 1 to 3? So the problem with that is this is going to be a repeated operation. The problem description says that this operation is going to be done multiple times. So if I simply just get the range sum every time in linear time, I get the range sum, when a caller asks me, then I'm operating in linear time in all cases of range queries. So the problem with this is we are wasting our time repeating the addition of items we've already seen. So we are duplicating work. When we're optimizing algorithms, we think of the bottlenecks, the unnecessary work, and the duplicate work. And this is from the book Cracking the Coding Interview. So what we need to do is we need to think, how can I save my work that I already do summing the array, and how can I get the sum? If I remember the running sums of this array, then after I get the running sums at each position in the array, then I can know a range sum in constant time. And the key is constant time. Whenever you get a problem that says a question is going to be repeated, or there's going to be repeated work, a call is going to be made multiple times, what we want to do is we want to find a way to cache items, because what we want is constant time access to an answer. We want the answer to a problem to not have to scale with the input like linear time does. So what we're going to do is we're going to build a sumCache. So let's see what that looks like. So what we're going to do is we're going to find the sum at the position or up to the position in the original array. So what we do is we index off of 1. The reason we add this position here is so that for convenience's sake, we add this extra position in the front. We don't really need it, but you'll see in the code, if you look in the description, it's a lot more convenient to have this extra position in the front for indexing purposes, and you'll see what I mean soon. So what we need to do is we need to populate this cache, and what we're going to see is that at this position, we're going to know that the sum going from 0 to 0 is going to be the sum here. The sum here is going to be the sum from the beginning all the way up to this position. The sum here is going to be the sum all the way from the beginning up to that position. So let's populate the cache right now. Okay, so what we're going to do is we're going to put our first iteration right there. We're going to put I right there. Okay, and the equation for the way we fill this out is the cache at the position of I plus 1, I is sitting at 0, the position right here, which is the running sum up to there, see how these map to each other? The reason we're adding 1 is because we added this first position, and now we're indexing off of 1. We pushed the array forward. So the amount or the running sum at this position is going to be the sum of the actual item, which I is sitting at the actual item, sitting in nums, plus all of the sums coming before the position where the item sits. So what we do is we access the cache at I as well. And again, we're doing this because we're indexing off of 1. If we were not indexing off of 1, we would have to say cache I minus 1. So what we're going to do is we're going to do 1 plus 0 equals 1. So at this position in the cache, at this position, the running row sum at that position is going to be 1. And as you can see, they map to each other. That's correct. So we advance I. Okay, so what is this position's row sum going to be? So what we need to do is we need to see the value of the item. It is 2. So what is the sum of all the items coming before this? So that is going to be right here. It's going to be 1. Each index in this cache indicates the running row sum of all the items coming before the item sitting at this index. So the sum of all the items coming before index 1 is the value of 1. So what we do is we do 1 plus 2 is 3. So now we advance I. And now what we do is we do the value of the item plus all of the running row sums coming before that item, which is the same index in the cache, because each index in the cache means all the sums coming before the same index in the nums array. So the same index 2, all the sums coming before index 2 in the nums array is 3. So what we do is 3 plus 3 is the running row sum at that index. So it is 6. So now we have a cache of all of the running row sums. So this is the way we access our cache after we have built it. If we want the sum from 0 all the way up to a certain item, what we need to do is we need to do the index plus 1. That is going to give us the sum from 0 to that item. So what I'm going to do is I'm going to do 2 plus 1 is 3. I access the cache at 3. What is the value of the cache at 3? We see that it is 6. So the sum from the beginning of the array to that item is 6. So what is the sum from the beginning of the array to 1? So what we do is we do 1 plus 1. And then we get 2. We access the cache at 2. So what is the value now? The value is 3. And we see that's correct. And if I want to go from index 0 to 0, then I do 0 plus 1, which is 1. I access the cache at index 1, and what I get is 1, and that is the correct answer. So now you may be asking, how is this going to give us constant time access to a range sum? So all we need to do, if I want the sum of the range from I to j, if I want the sum from 1 to 2, what I need to do is I need to get the sum from 0 to 2, and after I get the sum from 0 to 2, I need to get the sum from 0 to 0. And I want you to notice, do you see how the desired region is right here? Let me show it. So I just drew a line up here of the region we desire. So what is this region going to be? So this region is going to be this huge region, which has this element here that is not in the desired region. What we need to do is we need to take the big region and subtract the little region from it, and then we're going to get the region that we desire, and it's going to look like this. And now that is the answer to our query. So what is this in terms of indexing? So what we need to do is we need to get the sum from 0 to 2. So what do? I need to access the running sum for the upper bound. So how do I access that? Remember, we do plus 1 because we're indexing off of 1. So what we need to do is we need to do 2 plus 1. So what we do is we access the cache at j plus 1. And now we need to subtract away the region that we don't want, that lower region. And the way we do that is we subtract all the region going all the way up to the left bound. So we need the region going all the way up to the left bound. So what do? We need to access the cache at I. And why do we access the cache at I? So if we access the cache at I plus 1, we would be excluding the lower bound itself. So what we need to do is we need to go up to I so we don't exclude the left bound. So this is what that looks like. We get the bigger sum. We get the smaller bound. We get the lower bound. We get all of the items before the lower bound. And the higher bound sum turns out to be 6. So we take 6. And from 6, we subtract the lower bound sum. So what we do is we subtract 1. And what we get is the answer of 5. So this is the gist of this question. Again, code is in the description. It probably describes this better than I could even do it here. I have a walkthrough also in the code in the description. So our time complexity, if we didn't have a cache, would be linear time always. But to build the cache, it's going to take linear time, and then afterwards, we're going to have constant time range sum query access. After we have the cache, we're going to have a constant time access to our range sums. So the space is going to be linear because we're going to be keeping a cache of the range sums. And although we include an extra indice at the front, we don't have to do that. It's just easier and more convenient. So this is the time complexity, and that is the space complexity for this problem. This was a pretty straightforward problem. So that is all for this video. Again, the code is in the description. It is a great explanation of this problem. If you like this video, hit the like button. If this was a clear explanation, subscribe to the channel. We have more software engineering videos to come. And so I could talk more about the other applications of this problem, like the applications it has for 2D matrices and finding the sum of a rectangular region, which is similar to a problem we covered in finding the largest rectangle sum. But I'll leave that for another day. I think this is enough to understand and solve that problem without having me cover that. So that's all for this video, and what...